So very good morning. Now we are going to start our session 5. Okay, that session will be discussed by Jayadev. He is a PhD scholar, senior PhD scholar in our department. He is going to deliver his presentation on different application and design for integrated multi-input converter for DC microgrid application as well as DAV converter, their switching techniques based on that. Okay, Jayadev, over to you. You please carry on.
Thank you, sir. Good morning, everyone. In this session, we will discuss about the designing and application of integrated multiport converter, uh, which can integrate PV, pico hydro, and battery, uh, and also supplying DC load along with the AC load. And between, we will discuss about the DAV converter design also and its different switching technique. In this session, I will go through all this content. Let's start from the introduction. Why we are now more focused on the uh, multiport converter or integrated multiport converter. As we know, the need for sustainable energy has driven interest in renewable sources like solar, wind, tidal, biomass, hydro plant. It's a alternative to the fossil fuel. Because of we are more focused now, we are more focused on clean energy. That's we are more focusing on the renewable sources, how you will use efficiently. The renewable energy usage grow in last decade. We'll see the renewable energy grow very rapidly. With this, we need to integrate more than one renewable source in a single converter. That will become very essential because some of the renewable energy like PV, wind, these are intermittent in nature. Like PV depends on the solar irradiance. Wind is depend on the wind energy system is depend on the wind flow. And like a pico hydro, if we take the hydropower plant, it's depend on the rain and the water flow. So these are not in our hand. So what we do to eradicate this problem, so we do what we do, we will integrate more than one sources, so that if one source is unable to supply the sufficient power, then other sources will supply the demand. This configuration, in time we'll discuss about the one particular configuration that will be integrated multiport converter. You can say this converter will supply, uh, it has some advantages over the non-isolated or single multiport converter. Like it has multiple power channels, independent power flow, inherent voltage boosting, and it can support sub switching that can help in achieve maximum efficiency. Because of this intermittent nature of renewable sources, we are integrating more than one sources. But integrating more than one sources is a very challenging part also, because power managing between the sources and the converter, exact design of the converter become the very essential. If your converter design and efficient power management is not there, then enhancing the stability is very difficult, and reliability of power supply also very difficult. So to achieve all these things, we need efficient or effective energy management and efficient converter design. With this, we can achieve uninterrupted power supply to the load, optimizing the use of available renewable sources, and increase the stability and reliability of the power system. Then the objective of this session will modeling and design of different converters that are used to integrate all the sources, uh, and successfully will integrate PV, pico hydro, and energy storage system, and that can supply DC load as well as the AC load. And we will implement some design and implement some control algorithm to stabilize the DC link voltage. And later we'll discuss about the DC DAV converter design and some modulation technique. How different modulation technique will help the DAV converter to achieve its optimum performance. Coming to the block diagram of the system, this figure represent the overall block diagram of the system that we have designed. Here we have used PV and pico hydro as sources and battery to stabilize the DC link voltage. We cannot connect directly sources into the DC link because all the sources, their output power and output voltage are different. So we need a common point to integrate all the sources, or you can connect connect parallelly. So to do that, we need some interfacing converter. Some we need DC-DC converter, sometime it will be AC to DC converter. Like as a PV is a solar PV is a DC power output sources. We need a DC-DC interfacing converter. We can use boost a buck boost or a septic converter. Here we are using septic converter. Why you are using septic converter? We'll discuss this later. And for a pico hydro, the output of the pico hydro is a AC quantity. So we need to convert into DC. Then or either it is stepping down or stepping up. It depends on the your system, energy system. So we are uh, designing this at the low DC link voltage around 220. That's why we need here a buck converter. So after converting AC to DC quantity, then we'll step down the DC voltage to a required DC link voltage, and we'll integrate this to DC link. Then for battery, these two PV and uh, pico hydro, these two sources are unidirectional. So we need converter that can supply that will have unidirectional power flow capability. We don't need power directional capability, but in battery we need bidirectional converter, because the battery purpose is to stabilize the DC link voltage. So whenever it is needed, it can supply the uh, energy to the DC link voltage to stabilize the voltage. And whenever the DC link power is more, then it can extract from the DC link so that the voltage will remain at the uh, limited, or the DC link voltage remain constant. Coming to the DC load side, we are using DC load as well as the AC load. DC load we can connect directly to the DC link. For the AC load, we need an inverter, like which can here we are using a three-phase inverter which is operated at 180 degree mode. We are not using as PWM or something to make it more smoother. For the basic purpose and for the conversion purpose and make it too simple, we are using only 180 degree mode. This feature have some inherent advantages compared to the others, like a different power flow channel. As the individual or a particular converter is assigned to a particular sources, the power flow path from the input to the output is different for different source. Means whenever one source is supplying through or supplying power to the load, then others at the same time the other source can also supply. Though there is no cross link between the one source to other source, we can say independent power flow path for improved power management. Whenever you go for the power management, so this point is very much necessary to should have independent power flow path. If let's see, if one converter is connected to the two sources, means one switch is responsible for the two source to extract power from input to output, then at a particular time only one of source is able to deliver the power, and the trace upon the switch also increases. So for the high power rating, that configuration is good for the low power rating. For the high power rating, we need the individual converter to integrate the different sources. And here we are using DAV converter to integrate the battery or storage system. We can use buck boost converter also, bidirectional buck boost converter, but we are intentionally using DAV converter because the DAV converter have inherent some advantages over the bidirectional buck boost converter. It can if you used bidirectional buck boost converter, the your DC link voltage will be fixed. Once your converter is designed, then your DC link voltage is fixed, and your switching range is limited. Means you can say from the input to output voltage range will be limited with the switching range. That means your duty cycle. But in this case, what happened, as the DAV converter is consists of a high frequency transformer. So secondary side we can use multiple terminals at multiple voltage level. So for this particular design, we can have multiple DC link voltage to integrate. Means you are designing now it is 220 volt. In future you are planning for increasing to 400 volt. At that time also that single converter and same transformer uh, will help to integrate the battery also.
Sir, one question.
Yes, yes.
Hello. Sir, can be DAB is used for multi-port or for if more than voltage for different rating? It is
More
multi-port
than
or
voltage means
one
at
volt?
it has a one transformer na. So
Yes, sir.
you can have a tapping at secondary side. Means
Okay.
you are giving 48 volt, your tapping will be 110 or 220 and 400 also according to your transformer design. But you cannot use at a time at a different DC link. If you are
Yes, yes.
using
Okay.
at 220 volt, you
Hmm.
can use only 220. And later,
Okay.
if you want to use that 400, up to 400 you can use. That doesn't mean you are using 400 one DC link and 220 as one DC link. That will be
At one time only we can use only 1 volt. No?
at
Okay.
one time you can
Hello. 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 Hello.
Hello. Anything happened? I am not hearing any sound or video is not coming.
Yes, ma'am. Maybe disconnected. Jayadev, ma'am, sir. Maybe disconnected.
Okay. From your part, no? It is from your part.
No, no, ma'am. I'm also attendee. Maybe from organizer side.
And the speaker has somehow disconnected.
Yes, yes, ma'am. Yes, ma'am.
Okay. Okay.
Am I audible now?
Yes, sir. Yes, sir.
Yes, sir.
Okay, sir. Thank you. Yes. As you discussed in case scenario 1, the power coming from the PV, it fed to the DC link voltage through the SEPIC converter. And that DC, from the DC link, we can supply both the
Not visible.
Sir, your screen is not visible.
Slide.
Sir, your screen share has stopped, sir.
Okay, sir, let me check
It is not
once.
visible.
Is it visible now?
Yes, sir.
Yes, sir. Yes,
Yes,
sir.
yes. Now it's visible.
It's visible, but not in full screen mode. Yeah,
Yeah,
now it
yeah.
is.
Actually, I have a question here.
Yes, yes, please.
Actually, like, why have you used like bipolar DC link? Like, mostly, like, we can see that uh, seen that monopolar DC link has been used. If you can
Means
explain, please.
bipolar DC link means not bipolar actually. It's I am showing the positive and negative terminal only. DC link na or DC
Yes, sir.
supply. It's like positive terminal and negative terminal. That connection part will be clear so that I have shown that positive and negative. It doesn't mean bipolar DC link.
Okay. Got it. Thank you.
Okay, coming to the case scenario 1, when PV is available, the PV only supply the DC link voltage, DC link, and from the DC link will supply the load, both AC and DC load, and also charging the battery. Here in this case, we'll see the switching sequence. In the switching sequence, for charging the battery, the primary side should lead the secondary side voltage. You can see S5 and S8 each leading compared to the S1 and S4. We'll discuss this switching sequence in the DAV converter. When we discuss the DAV individually, we'll discuss how this leading and lagging will vary according to the power supply. We'll discuss this one. For now, we can see the switching. But in this case, when you integrate the multiple converter, you need to consider one thing, that all the switches those are connected to the source should be at the same frequency. Here you are using 20 kilohertz to trigger all the switches. All the frequency are the same except the inverter. Those are on 50 kilohertz only. Sorry, 50 hertz only. Coming to the case scenario 2, here both the sources, if you plot the circuit diagram or connecting all the switches and sources, it will looks like this. And PB and Pico hydro both are supplying the DC link and the battery. In this case, the three-phase supply first converted to the DC, that will be one pulsating. That's how you use a capacitor to smooth it out. Then step down to the required DC link voltage. And from the PV, that's a peak converter used to extract the maximum power, and that fed to the DC link. And from the DC link, we are supplying the load and the battery. Coming to the case scenario 3, in this case, the PV is not available till, but the Pico hydro is connected. This will be sufficient for supply the load and the battery charging. In case 4, when all the sources are not sufficient to supply the load, at that time battery can support to meet the demand. At that time, the switching of this battery will see the S1 and S4. S1 and S4 each leading, means secondary side is leading in the to the primary side switching voltage. At that time, the power is supplying from secondary to the primary, and it will supply the both the load AC and DC. Coming to the modeling of the SEPIC converter, as we know, this SEPIC converter, it consists of two inductor. To designing these two inductor is very crucial. Why use the SEPIC converter, not the normal buck or boost converter? It has some inherent advantages over the PV system. It can handle a wide range of input voltage, make it ideal for variable solar condition. Means we know in a single day, the solar irradiation is changing. The level is power generation level also changing. At all the changing of solar irradiance, the power level also different. At all the power level, to track the maximum power, means to extract the maximum power from that low and high solar irradiance, we need a converter that can have a large voltage range area, means that can operate in a large voltage range area. Means sometime it will be buck the voltage, and means it can go up to the less than the 0.5 duty ratio, and sometime it can go above the 0.5 duty ratio, so that it can step sometime and it can step down or step up also. With both the cases, as this converter can support both the cases, so of tracking maximum power at all the irradiance value is easy compared to the normal buck or boost converter. But designing this parameter LS1 and LS2 is very crucial for this operation. So how we design it? So first, we actually basically use the equation 2, that gives the inductor in terms of ripple inductor current and the voltage. Once we decide the output voltage and the input voltage, means our solar system solar module is known to us, and the DC link power DC link voltage is known to us, so we know the input and output voltage are fixed. Then the switching frequency, you have to decide a switching frequency at which you want to operate. Means if you are going to implement this system in the hardware, so you have to consider the hardware specification of the switch also. And you have limited into the simulation, so you can go to very high frequency, so that your inductance value will be less. For the hardware, if you want to experimentally, then that choosing the right frequency is very important, because all the components, mostly the whatever we are using IGBT modules from Semicron, those are operate a maximum frequency of 20 kilohertz. So what we did we design this system to operate up to the 20 kilohertz. So we choose in between 10 to not less than, not very less and not the towards the maximum. So we choose in between. It's around 15 kilohertz we choose frequency, and we design all the inductor value. So once you know the input voltage, your frequency, then you have to find the uh, ripple in inductor current. How do you do? So ripple inductor current, what you do? You choose a percentage of the current. As a LS1 is connected to the source. So source current, the how much percentage of a source current will be your ripple current, that you have to assume. Normally we choose around 20%. For the safer side, we in design purpose in hardware also, we choose around 20% of the average current, and we decide the del IL value and the D value. D value also fixed once H, your input and output voltage are fixed, and D also fixed. So you can find L value. That L will be the inductor will be your minimum inductance, so that your converter will operate at a continuous conduction mode. So you need to take more than that inductance value. Similarly for the capacitance also. For capacitance case, what you do, uh, you choose a del VC, means your output percentage. Normally what you do, we choose around 3 to 5% of the uh, average voltage, and we design that as capacitance value. That again, that capacitance is your minimum value, so you have to normally will take 1.5 to 2 times of the design value. So in this way, we'll find the L and C value. Once we'll check in the open mode, then we'll connect the PV, and again then we integrate into the DC link. Coming to the buck converter, similar way, we keep in mind what type of system we are going to integrate with this buck converter. For that, we take the machine rating, how much rating machine we available in the lab, and compared to the, keeping in mind that voltage will decide the of V naught. V naught is your DC link voltage that will connected uh, that will be connect in your output side of the buck converter. So in this case also, we will decide that ripple inductor current del ILB, that is also 20%. We take 20%. Maximum we can go up to the 30%, but we will take around 20%. And the same for the del V naught, ripple voltage across the capacitor. That will also take 3 to 5% of the output, average output of the system. In this case, we will design the inductance value and capacitance value for the buck converter also. Now coming to the modeling of DAB converter. As you know, we have used DAB converter uh, compared to the normal buck boost converter. It has so much advantages. Along with the advantages, it has some complexity also. I can give you a brief about the DAB converter. DAB converter nothing but it consists of two full bridge converter connected with a high frequency transformer, and all the switches are operated at 50% duty ratio. And how the power will transfer? The power will transfer from one terminal to different terminals, means from input or from output to input. It depends on the only phase shift between the bridge voltages. Means transformer, if you find the voltage across the transformer, that is the bridge voltage. That bridge voltage phase difference from primary to secondary, that will only decide the power transfer from any side. Once your inductor is fixed, means once you design the DAB converter, your inductance value is fixed. So only the deciding factor is your phase difference. And at one phase difference is plus minus 90 degree. At that time, the DAB converter can transfer the maximum power from one end to other end. If you simplify this circuit, figure 5 will simplify, then figure 6 will represent the exact equivalent circuit of the DAB converter, where you will see two sources are connected through a inductor only. So phase shift between the two sources will transfer or will monitor the uh, power level, how much power you want to transfer. That will be decided by the only phase shift. It has some inherent advantage compared to the buck boost converter. It's provide high efficiency bidirectional power flow. Means your bidirectional power flow is very efficient. You just convert, you just monitor or change one parameter, your bidirectional power will be of flow. Means if you want to supply, you want to transfer power from input to output, then you want to transfer power from primary to secondary, then primary voltage should be leading to the secondary voltage. And similarly, if you want to transfer the power from secondary to primary, then your secondary should lead the primary. Means you just change the phase shift from the primary to secondary bridge voltage, from lagging to leading or leading to lagging. That's it. From that only you can transfer the power from both end. Means the power transfer become very much efficient. That's why
Sir,
the
one
DAB
point. Is that condition
Yes.
should be 90 degrees or plus or minus 90 from primary to secondary and secondary to primary?
Yeah, plus or minus 90 means plus 90 means is transferring from one end to different other end, and minus 90 means from other end to this end.
Thank you.
Like
Thank
that,
you.
that's why we have mentioned plus minus 90.
Sir, as you have shown in the cases, last
Mhm.
case you have discussed,
Yes.
when all the sources, when the load required more than the generating voltage, generating power. This DAB
Yes.
is working from secondary to primary side, na?
Yes, sir.
At that time, we have to change the phase shift, na, in the program.
You have to change the phase shift from lagging, leading, whatever earlier, you have to reverse the phase
Means
shift.
secondary will be leading and primary will be lagging.
Yes, sir.
Okay, sir. Thank you. And sir, the all the switches, the second point, 50 for asymmetric duty cycle, duty ratio, it may be different, na? It may be 40%, 30%. This is for symmetric duty. Hello. Hello. Hello.
I think Sarah has been disconnected.
Hmm.
Now it's audible, right?
Yes, sir. Yes, sir. It's audible.
My screen is visible or not?
No, sir. It is not visible.
Okay, one second.
No, sir. It is visible.
Visible, right? Okay, okay.
Yes, yes.
So we are discussing the SPS control. In this control, what you do, will make a single phase shift between this primary bridge voltage and the secondary bridge voltage. So normally what happens, this diagonal switch are combinedly on, and in a single leg, one switch is means S1 is complementary to S4. Like that, all the bridges are same. Diagonally, we combinedly on and off. And in single phase shift modulation technique, what you do here, if you see S1, S4 are turning on at this point, but after some phase shift phi angle, we signal this S5 and S8. Means there is a phase difference. If you plot the if you plot the voltage across the bridges, what you got, VP, say the primary bridge voltage, and VS is secondary bridge voltage, you will get a square wave of this way, and the secondary bridge voltage, you can see a phase shifted by phi angle like this. And similarly, the inductor current, how we get the inductor current, the voltage difference between the bridge voltage will decide the inductor current slope and the value. At this phi angle, in between phi angle, the voltage difference is more, so the slope is high at this time. But from this point to this point, voltage difference is not that much high, and hence the your as it is positive, so the slope is positive, and the slope is not high, it's less. Similarly, all the remaining time, this will operate in the similar way. And the equation 7 decide the how much power will flow. Means this equation represent the power versus the phi angle phase shift. How much phase shift will decide how much power. Means how you if you want to design this inductor, leakage inductor here, the designing process is very much crucial. So first you need to fix the frequency, and as you know the primary and secondary voltage, then what you do here, you first calculate how much maximum power uh, can be transferred. Or if you already decided the power transfer, means you are designing a DAB converter for 1 kilowatt, then your power level is 1 kilowatt. According to your 1 kilowatt, you will choose the all the switches and the inductor wire, everything you have to choose according to your 1 kilowatt. You know the voltage, then you have to decide the how much current the inductor will flow. According to the inductor current, you will decide the inductor wire, that gauge value, how much gauge wire you need to wire you to design the inductor. Once your power is fixed, then what you do, you check the maximum inductance, at what condition the inductance will be maximum. Means if you choose phi each pi by 2, means at pi by 2 the power transfer will be maximum from primary to secondary or secondary to primary. At that time, how much maximum inductance that can be used, you can calculate. Once you got the maximum inductance value, then what you do, you decide your operating range. Means normally we use what you do, ki 1 kilowatt, if you are using 1 kilowatt system, we hardly use up to the 600, 400. We know, means up to 400, 600, it can efficiently or it can work easily for a long term. So what you do, you decide the power range, and that power range, how much uh, phase shift phase shift will you got, you can calculate from this equation. Once you got the phase shift, at particular phase shift, a particular power will be transferred. It means you can find the range. In between range, you according to your application, you choose the phi value and L value. This single phase modulation technique is very much simple to implement, but it has some disadvantages like circulating current. Means even if your output is open circuited, internally there is a circulating current. As you see, in whole time, your phase difference will be there. Phase difference between the primary and secondary across the inductor will be there. Because of that, the inherent the current will circulate between them. So to reduce this circulating current or to improve the efficiency, so what we do? So we will go for the double phase shift modulation. In this case, double phase shift modulation. In this case, what we do? We implement two phase shift between the bridges. Means in single phase shift, we are using single phase shift between the primary and secondary bridge. But in double phase shift, what you do? We implement a phase shift between the primary bridge and secondary bridge, that is outer phase shift, as well as a phase shift between the lag. You can see here. We are giving additional degree of freedom. The outer phase shift, same as the single phase shift, that phase shift is in between the bridges, primary and secondary bridges, and the inner phase shift theta. Inner phase shift theta will be provided. The phase shift between the legs of one bridge. Means, see, this is S1 and S3 is connected in a single leg. So S1 is complementary to S3. You can see here. Yeah. S1 earlier, S1 and S4 both are switched on simultaneously, means at a time. Now what you do, we'll give a phase shift between the S1 and S4. See, in figure 8, it's a double phase shift modulation technique. One phase shift phi in between the S1, that is primary bridge, and the S5, that is the secondary bridge. And the other shift
Hello.
theta.
Sir, yeah, the voice is coming from Dr. Madhumita. Hello.
Yeah, voice is coming.
Please carry on. I have muted her. Please carry on. I have muted. Jayadev, please carry on.
Yes, sir. Yes. In double phase shift, one phase shift for the both bridges voltage and other phase shift we are giving between the leg. Means S1 is connected in one leg and S4 is connected in other leg. Earlier it was turn on simultaneously, means at a time there's S1 and S4 where we are giving same gate supply to S1, S4. But in this case, double phase shift, what you do will give different pulses, which is phase shifted by one angle theta. Same thing we'll do in the secondary side also. A phase shift between the S5 and S8. This is called a double phase shift modulation technique. So in this case, what happened as the phase shift is more, means two extra phase shift we have incorporated. So because of that, the current is smooth compared to the earlier one. Compared to the SPS modulation, the current is bit smooth, means that slope will be not that much sharp. It will be less sharp than this one. So because of that, the voltage difference across the inductor will be at that time will be less compared to the earlier SPS control. So hence the current flow also comes. So current flow also less. In this way, we can reduce the circulating current in this case, but we cannot eliminate completely circulating current in TPS modulation. So what we do? We use a TPS modulation technique. In TPS modulation technique, what we are doing? In DPS, what you do? We implement a outer phase shift between the bridges and a inner phase shift theta between the leg. So in TPS, what you do? That inner phase shift which were incorporated between the leg, that phase shift amount is same for the primary side leg and secondary side leg, bridge leg. But in TPS control, the phase shift is dynamic, means it is not same for the primary side and secondary side. It vary accordingly. In this case, if you implement the closed loop control according to the voltage, means at what time the voltage will be there and the current requirement is there, according to that the phase shift will change. So in this way, the current dynamically you can reduce the uh, circulating current more compared to the DPS control. But with this complexity also very much increases, means in hard experimental you want to implement TPS control, it is very difficult. You need very much expertise on this. For simplicity, what we do? We are using only this SPS control. At our system, we are operating at 1 and 2 kilowatt. Then SPS modulation technique also work fine. At less power level, in light load condition or low power level, the SPS control have much disadvantage compared to the others. So for simplicity, we are using SPS modulation technique. So as this DAV converter is used to stabilize the DC link voltage. So to do the voltage control, we need one controller so that the voltage will be stabilized. For that, what you do? We are designing a PI controller. So basically, you can design mathematically PI controller, but we are using, as we know the transfer function, so you are using MATLAB CISO tool. I'll show you how to design the transfer function also in MATLAB. Sorry, PI controller in MATLAB from the CISO
Sir,
tool.
this is the transfer function of DAB.
Yeah, this is the transfer function of the DAB. I have this is not done by me. I have incorporated from the a paper which I have referred as in 10 reference. From that paper,
irrespective of any modulation technique.
Irrespective of any modulation technique, because the transfer modulation technique only for the switching only. Your transfer function will decide your component. So once the converter is built, your component is fixed, then the transfer function is also fixed. This is the
Thank you, sir.
for voltage control. We have using this transfer function. At this gives the voltage with respect to the phase shift.
Okay.
So by using the MATLAB SISU tool, we have designed the PI controller for this to stabilize the voltage. With this, we got the PI value KP as a
Sir, what is
0.22.
MATLAB CC control?
MATLAB SISU tool means I will show you in the MATLAB. So
Okay,
how
okay, sir.
to,
Okay.
if
Okay,
you know the transfer function of a particular converter, so you can design means a basic classical controller in the MATLAB SISU tool only. You no
Okay, sir.
need to go for the mathematics, complex mathematics or the trial and error tuning.
Okay, sir.
With this, we have got the body plot and the step response. This is the simulation parameter table 1 source. This parameter we have used in the simulation, but however it is a bit different that the 20 kilohertz were not considered. We have considered 15 kilohertz only, and the DC bus voltage we have taken 110 instead of 220. So before coming to the result, I'll show you in MATLAB. Is it visible?
Yes, sir.
Visible,
Visible. Yes, sir.
Jayadev.
Yes, sir. Yes.
Yes. Here you can see this is your SEPIC converter. It's connected through a PB. And for Pico Hydro, we have using three-phase source and then DAV converter. Sorry, die bridge rectifier FET buck converter. Then other source is a battery. From the battery, we are giving DAV. From DAV, it integrated into the common DC link. All these sources are integrated in the common DC link point. These 2 points, all sources are parallel.
Hello.
What is this?
Yes, sir.
Have you considered Pico as like a three-phase source, like alternator?
I have considered Pico as a three-phase
Right.
source
Like alternator.
because in our laboratory, the Pico Hydro we have, that is three-phase alternator only. So because of that, I have considered three-phase source in the simulation also.
Okay.
Here, the SEPIC converter will track the maximum power from the PV. So in PV array, you can set your different value or predefine. Predefine, you can check or you can define your own only. User define, you can define your over voltage, short circuit current, so that your per panel, what will be your maximum power. So in this case, if you plot this now at 1000 watt per meter square and specified temperature, we'll plot, then we'll get the PV curve, both PV and IV curve. We'll see at this point. This system, whatever I have using, this system will give 981.45 at the maximum power at 120 volt, and at that time the current will be 8.13 amperes. Yeah. With that, you can define. I have used constant irradiation value and constant temperature to simulate this one. Then what I sense the PV voltage and PV current. Then I have implement the PNO algorithm to track the maximum power. So in this case, we'll sense the voltage, current, and we are externally giving the incremental duty at a time in a simulation. How much? This is the code for the maximum power generation with PNO algorithm. This is a simple one. That's why we are using PNO algorithm only. Then from PNO algorithm, this will generate the duty.
Hello.
Yes,
Am I
yes,
audible?
yes, sir.
I have a question. Like you have
Yes.
considered like constant irradiation and constant temperature, I guess.
Yes, sir.
So, is there any need for a MPPT in that case?
Means, see, first we have considered the constant value, but later in time we have changed the different irradiation and temperature value also. That result already
Okay.
taken. I will show you that result also. For the simplicity,
Okay,
what
that
you
will
do, we take the maximum irradiation, means standard temperature and insulation value, so that the whatever your PV is installed, means whatever your PV supply you are considering, that the maximum power that can achieve or not, whether your logic is correct or not, you can verify. If you change the irradiation value, so what you do, you need to check other at that irradiation value whether your power is, how much power that is giving or not. That you have to check. So for the simplicity and for the testing purpose, you use constant irradiation and constant temperature.
Sir, maybe MPPT can be used to. Hello.
Sorry.
So maybe MPPT can be used to regulate the load also, na? If the irradiance is constant, you have taken constant, but load is changing. So MPPT works in that condition, na?
Maybe some MPPT work in that condition, but in this case, as we are integrating more than one sources, na? So whether load changing there, then that will be take care by the other source only. Means if my motive was, what is my motive? If I am installing the solar at a particular radiation value, that the solar power should be maximum. If the load demand is
Yes, sir.
whatever with the load demand, then what I do, I will give maximum power from the solar only. Then I will use the other sources.
Okay.
are you using any energy management here? Like is the part
In this case, we are not using any energy management for now. We are only stabilizing the DC link voltage.
okay.
Okay, after this function, PNO algorithm, it will give the duty, reference duty for the MPPT tracking. That will be converted through the PWM generator, and it will generate a PWM signal of frequency. Whatever frequency will give here, time period, that will generate at that frequency with the required duty ratio. That duty will given to the SEPI converter here. We'll see SEPI converter 1 connected here. And this connected to the DC link voltage. Similarly, we have taken the 3 source as the pico hydro. Then it's connected connected to the rectifier module. From the rectifier module, we have connected the buck converter. From the buck converter, the output is conducted in the DC link. And similarly for the battery, what do? We can define the battery level, whether it is lithium ion or lead acid. You have to define here, and the rating, how much nominal value, how much of the capacity you have to you can decide. If you want more control, you can also implement the discharging characteristic also. But for time being, we are not using the discharging current. We are simply using the capacity and the voltage only. From the battery, we are connected to the DAV converter. This DAV converter is already shown here in transformer. That leakage inductance is incorporated inside the transformer. You can see here 48 micro Henry that is incorporated. That's why it's not showing outside. So from this DAV converter, we have connected into the DC link, and from the DC link, this resistive load considered as the DC load, and from DC link we have connected to inverter configuration. The inverter is operated at 180-degree modes, and from the inverter we are giving a AC load. This AC load also a resistive load only. For timing we are using AC resistive load only, and all the waveform will be shown here. Will be output and the control in. Coming to the control unit, what you do first to control this DC link voltage. This DC link voltage, we need to sense the DC link voltage that will sense from VDC. This is go to statement. This is sense output voltage is sense. It's given as a reference. Is given as a actual signal, and it is compared with the reference 220 volt. Inside we'll see. The reference signal is compared, then the error will fed back to the PI controller. We have used a saturation to limit the value, and the gain. This gain is decided. DAB converter. The main is phase shift. So this PI controller will decide how much phase shift it will require to transfer the amount of power to stabilize the DC link voltage. This is the function of the PI controller here. So then how you give the phase shift? To give the phase shift, we need we have using variable time delay block. What is this block? This block will take two input. One is for the reference, and other will be phase shifted by some time T0. That time you have to decide. So this will give in a radiance way output. Then we'll multiply with the multiply with the time period. So overall the time, how much that phase shift is converted into the time, and that will we are given into the variable time delay. So this variable time delay block, what you do, it will compare the reference signal. Means we are generating a 20 kilohertz signal with 50% duty. That signal that will be compared with the second one, and that signal will be phase shifted by whatever given in the PI output. Then that will be fed back to the secondary bridge. One for 5 and 8 switch, and that inverted one will be given to 6 and 7. As it is SPS mode, that's why these two switches are combinedly switch on and switch off.
Sir, screen is not visible.
Not visible.
Yes, sir.
Is it
Screen
same?
is not visible. I thought that it was only for me, but
Oh, actually, today we have some network issues. Sometimes it's a disconnect. So if anything happen in future, you please let me know immediately. Okay, let me check. Is it visible now?
No, sir.
No, sir, no, sir.
Not visible. Is it visible, sir?
No, sir.
Yeah, till now not visible. Not yet.
No, sir. No, sir.
Now it is visible.
Yes, sir, it is visible now.
Okay, sir. Thank you. So we are in the control unit. Basically, what you need to stabilize the DC voltage, we need to sense the DC voltage. So here VDC, from VDC we sense the DC voltage, and it will given to the PI controller in terms of error signal. So what you do, DC voltage you have sensed, then we will compare with the reference one. Inside we'll see this DC voltage and reference are compared, then error signal fed back to the PI controller. And from the PI controller, it will generate the reference of phase shift, and that each converted in terms of time, how much time that equivalent to the phase shift that will converted, then that signal will feed back to the time variable time delay. This variable time delay, what you do, what you did, this will take two signal. One is reference, above one is a reference, and below signal will take a reference time period. That time period will be phase shifted from the other one. Means here this signal, whatever with this signal, that will be phase shifted by the time we have given here in the terminal 2. That is the job of the variable time delay. So if you see inside, this is the generalized block. You no need to change anything. You just connect here. Here the PI controller job is to give the reference of phase delay value. That phase delay value is converted to the time reference, and that time is given to the time delay. So the whatever be the signal coming in first one, that will be phase shifted by this amount of time, and that will be given
Sir,
to the second.
Sir, the gain what you are using here is converting phase shift into time, means
Phase shift into
gradient
the
to
time.
time.
Yeah,
Okay.
that's it only.
It is by the frequency TS by 2.
TS
1 by T.
1 by T. Sorry, that will be 1 by F, means your time. You need to multiply with the time.
Okay.
So from the output here, we are given the pulses. Here you have to use a pulse generator that can decide how much frequency your switch will operate at what band pulse width as what duty. So you have decided 20 kilohertz frequency and 50 as a duty cycle for the DAB converter. This is directly given to the one bridge, and the other bridge given through the time delay variable. And this is the normal switching sequence for the inverter, that is 180-degree mode only. This is phase shift between the one leg to other leg only. Now coming to the result, with that simulation parameter and the setup, we have simulated and we got the result. Like we have tested first. Initially we have taken the standard value of irradiation and temperature. Then we change the irradiation's value, whether it is tracking or not, to check whether tracking or not. So in C, you can see in the figure 12 the tracking level of the power, as it is a PV source. The from input to output means from around whole day, the PV voltage will be around, it should remain at constant, near to constant at any irradiation condition, means not at zero, but obviously. So you can see 1000, we have changed 1000 to 700, then 500. We'll see the current value which changes, but the your voltage remains same, and the power accordingly, the power also change, but it will tracking the maximum power, and it is a PNO algorithm. No optimization is used. That's why this variation are much visible compared to the normal case. So with this, then this figure 13 shows the SEPIC converter input and output voltage. It sends the that output this output voltage from the PV supply, and it will convert, it will boost accordingly to 150 volt, like that. And same way for the DAV buck converter, which is connected to the pico hydro, the input and output voltage are converted. Three-phase input are rectified and stepped down to around 150 volt. And similarly for and figure 15, you can see the DAV converter, the primary voltages with respect to your leakage inductor current, and it is a SPS control. The leakage current will be of this shape, and we have checked both the charging cases and discharging case. 16 will show the discharging case whenever the load demand is more compared to the source. At that time, the battery is discharged, and you can see the SOC level is decreasing while maintaining the voltage, and it's supplying some positive current. And in discharging case, in charging case, in figure 17, you can see the SOC level is increasing while the current reference became negative, and the voltage is maintaining at nearly at that constant value. So with this, we maintain the DC link voltage at 220 and around 5 ampere. We have given to DC load. For the AC, as we are using 180-degree modulation in inverter, this type of pulsating, this type of six pulse waveform we are getting, that is voltage waveform only. I have shown only voltage, phase voltage A, B, and C. And we have tested a different load disturbance and control disturbance. What do you do? We change the load to 20 plus 20% increase, and the decrease to 20%. In both the cases we have checked, but we have noticed the minor variation in the DC link voltage. And similarly for the CD case, we have check the control disturbance. Means you are giving a error to the PI controller. If you error is around 50% more and 50% less, then how the controller will decide whether the phase shift is very much difference, so that the DC link voltage is stabilized or not. That we have checked. With this, we got the very less deviation. That C and D will define the control disturbance of 50% increase and decrease. And in this setup, we have experimentally tested also. We have a real-time solar panel, rooftop solar panel installed, around 333 watt. At the time of testing, what you got here, that irradiations is 907 watt per meter square. At that time, temperature was 31 degrees Celsius. At that time, how much you got? Around 237 watt we are able to extract from the PV panel. That is, if you calculate theoretically, that is nearer to the maximum power at that irradiation. Then we have tested our DAV converter for charging and discharging in our experimental also in SPS mode. For that, in this figure 22 shows the experimental value of phase difference between the primary and the secondary voltage. You can see you have given the 30 degree phase difference, and with that 30 degree phase difference, primary and secondary bridge voltage with a leakage current also we have plot. That we can see in figure 23. We have seen, we can see the input voltage levels and output voltage level with the inductor current variation, leakage inductor current variation. And figure 24 shows the charging case. Whenever
Sir, DAB is working in step up mode, na? Boost mode. Here?
yeah, boost mode.
Okay, sir.
Primary is 12 volt, we are using battery and is boosting up to 78 volt.
Okay.
And this case we have given a 90 volt input to the DAB converter. Oh, sorry.
Sir, in which case?
Leveling, sorry. That's figure 24 leveling is a mismatch. This is the charging case only.
Okay.
This is a charging case. We have given input 90 volt in the primary side, and it is step down to the 13 volt, and it's charged at that time. It work as a charging, means to charge the battery we have given 90 volt.
Buck mode means.
Yeah. This leveling is reverse. Sorry for that. And figure 25, it's again discharging case. Discharging case is 12.1 volt to around 79 volt we have boosted. Whatever we have inductor DAV transformer, with that rating we are able to boost that with 12 volt that much only. So because of that limitation, it is limited to 79 volt only.
Okay.
So with this, we will conclude this session. So we have successfully integrated and tested both battery charging and discharging case. And in future, we can implement sub switching. We can implement in this DAB converter, and we can implement the advanced hybrid storage system like a super capacitor to take care of the transient period. And in future, you can implement the advanced power management or energy management to balance the power sharing between the sources.
Sir, one
These are the
question.
reference I have gone.
Sir, hello. Hello.
Yes, sir. Yes.
Sorry, you have shown the reference number 10, in which you have shown that DAB transfer function is there, no? Which reference you are using?
Yeah. Oh, that's a reference which is missing. Okay,
Okay.
that should
10
be in
is
the
number.
10. I'll share that reference in the group. The
Okay,
reference
sir.
paper I will share in.
And what is, sir, MATLAB Shisho pool you have told in that?
Yeah, MATLAB Shisho tool. I'll show you some that. You can type Shisho tool. Inside, you can give the transfer function of the converter, or you can directly open the window. Yes. Here, what you do here, you just go to the
Yes, sir.
edit architecture, then you will select which type of controller you want to design. Here, different controller is available here. So you need to know the PI controller structure. Like that, you have to select. If you select this one, this around of the PI controller structure. This is C is controller, G is your converter transfer function,
Okay.
and H is your normal unity. So what you do here, if you have your converter transfer function, put here.
இந்த எம்பி எம்என்ஐ என்ட் பண்ணி
Sir,
எந்த செமஸ்டர் என்ட் பண்ணா ஆல்ரெடி என்டர்ட் அப்படின்னு வருது. அப்பதான் ஏன்னா செக் பண்ணி பாருங்க. அவனு பேப்பர்.
Again. So what you do here in term of G, you can import your converter transfer function here. You can import once it is in your workspace now, it will show here. Then you can directly import here and click OK. Then it will be automatically show the step response, root locus, body plot, and the frequency response. It's better. I'll import. Okay, it's not supported in this system. That's why I'm not able to open.
okay, sir, no problem.
Okay, I will show you the procedure. Okay, in this way you will get the step response, and then what you do, you go to the tuning method. Here you can see PID tuning. You click on PID tuning and you select whether it is P or PD, whatever you need, just select here. And you decide your robustness or how fast will be your system, and like that you can vary and click on update compensator so that your step response will be variable in this here, like that, like this your step response will variable visible here. Then what do you want to tune more, then you can vary the poles and zero directly here. You move here, your step response will be moved like that. So in this way, you can tune directly. Graphically, you can tune according to your requirement.
Okay, sir.
Okay, sir.
Hello.
Yes, sir. Yes.
And sir, next question is, sir, you have used buck converter and DAB converter efficiency frequency at same frequency, na? You are operating both at same frequency.
Same frequency.
So you're supplying PWM signal from same controller to both the converter.
Yeah, from same control we are given supplying the both converter.
PWM
That yes,
signal.
we are using a C2000 microcontroller here, F23879D version, and that gets there are so many input output EPWM pin is available. So you can supply
Okay, sir.
as many.
To both converter from the same. Okay.
Yes.
Okay, sir. Please send that when you're free. Please send that
Yeah,
10 number
that,
reference, na? Okay.
yeah,
Okay.
yeah.
Thank you, sir. Thanks, sir.
Any other query?
Any other queries from the participants? Is
Sir,
there any other queries?
yes, sir. One last one.
Yes, sir.
Sir, regarding this implementation, like you have taken 4 cases now.
Yes, sir.
Which case to be implemented is totally depend upon the load condition. Am I right, sir?
Totally under the load condition.
Yeah, okay. Then, I mean, for example, how you proceed? Like, I want to have condition, I mean, case 1, case 2, how do you proceed? I mean, in the simulation?
I mean,
You check
simulation.
each case one by one, or you'll check, how do you do that?
Actually, if you want to implement, if you want to do automatically, you have to implement the energy management. So energy management logic will decide whether it is that logic will say in terms of source availability, whether you are implementing source availability or your real-time scenario, your weather condition, like that logic you have to implement in the energy management case. That will decide which case it will be operate. You want to do the manually, then you have to manually switch off and switch on the supply. Basically, we do use the energy management.
For energy management, do we need to write that code in FPG, or how do we handle this when you want to do it?
Actually, you want to do, then you have to write the code, or you can implement. You sense the power from all the sources. Once you sense the power, then you write a code key at what time, what power will be available at what percentage. Means if you are using the over a single day, at the morning the PV will be less, at around mid that will be PV will be high, and evening and the night. 4 condition you can check. Means not this condition whatever I have shown here, not this condition. You can simply take the in a single day what are the condition it will be available in real time. So according to that you write the code. PV will be less, means PV will supply 1/10 of the total power, and rest will be supplied by the other source. That will become the one case, and for few time that will be continue, and after few time the PV power will be more. Then at that time the PV will supply the 50% or even 80% of the total power. At that time the rest 20% will supply by the pico hydro or battery. Like that you have to write the code and decide the duration, how much duration, what type of logic, what type of scenario you are want to implement. As this is a simulation only na, so you have to write, you have to decide your scenario only. You cannot fit directly the real time now. So that thing you have to write in a code only.
Okay, sir. Thank you. Thank you very much.
Okay, sir. Any other queries?
Is there any other queries, so we can conclude the session now? Okay, I think there is no other queries.
Thank you, sir. Thank you.
Yes, yes. So we can conclude our fifth session. Okay. So okay. Thank you, Jayadev. So we are going to end the meeting now. Again, our meeting will be resumed 3 p.m. onwards. Professor Banibroto Mukherjee from IIT Kharagpur. Okay. He will deliver the lecture in the second half. Okay. Thank you, all of you.